All right, so another effect of having electrons behave like waves, and the idea behind the wave function is that electrons can actually teleport out of atoms, okay? Or even particles within atoms can essentially exist and have a probability of being outside of the atom as well as inside of the atom. So we're going to be looking at the concept of tunneling as the last phenomenon of wave-like properties of electrons. So in classical physics, in order for an object to go from a low potential to a high potential back to another low potential, you would have to put in energy, climb this hill, and then release that potential energy, allow that object to roll down a hill onto the other side. Well, atoms, if I was thinking about electrons as particles in an atom that is attracted to the nucleus, in order for me to remove that electron from the nucleus, I would have to supply energy to break those electrostatic interactions so that I can remove it. Okay, and this would be called a potential energy well, like we learned in HL gravity. So energy would be required to remove something from that potential energy well and raise the energy of something to infinity in order to remove an electron from an atom. Well, what we're going to be talking about is an alternative way to remove an electron from an atom, and that's through tunneling. So in classical physics that we talked about, like in gravity, you have to move things uphill and downhill. But in quantum physics, we have another way of moving electrons from atoms to atoms, and that's through the principle of tunneling. And what tunneling is telling us is that there's a probability of finding an electron here and here at the exact same time. So underneath here, we have that diagram I showed you of wave functions, and these are the different harmonics or higher energy levels. And if I square these wave functions, I get the probability functions for waves, and this tells me the probability of finding an electron in space. These dotted lines represent the barriers. It represents the well. Okay, if I'm beyond those barriers, I'm outside of the atom. And what you can see in all of these graphs over here is that there's a little tailing end of a wave function that exceeds the diameter of an atom. So even here, I can see that there's, a little bit of the wave that exceeds outside of the atom. And here's the probability exceeds outside of the atom as well. So there's a chance if I get close over there that an electron will be outside of the atom, but it's much less of a chance than what we see from inside of the atom. But there is still a chance. All right, so what prevents electrons from leaving or being beyond? And these are called barriers. Okay, the steeper the well, the steeper this well is, the greater that barrier is, and that wave keeps reflecting on itself. And what we can see here is that wave function, it exponentially decreases the thicker that barrier is. But if I can do something to decrease the steepness of that well or decrease the barrier width, what we'll see is that as that exponential decay occurs, it doesn't go all the way down before the wave function is allowed to participate. So if I had a particle that was traveling and bouncing back over here, well, a particle with enough energy can simultaneously exist outside of an atom as well as inside of an atom. And that's the principle of tunneling. So if I have a thinner barrier, okay, and there's ways we can do that by organizing materials or changing the temperature of materials, I can induce or create conditions where an electron can have a probability of being found outside as well as inside. And in that case, an electron can tunnel through a barrier, or an alpha particle in the nucleus can tunnel through a barrier and be outside of the atom. This is a really interesting phenomenon, and scientists around the world are trying to use this idea to design materials that would allow electrons to move incredibly fast through wires, through teleportation. And when we think about X-Men and all these other Ant-Man that talk about quantum physics to explain supernatural powers, tunneling is definitely one of the ideas that promotes a lot of good thinking for creativity. Here's just a little diagram illustrating what I'm talking about. If there's a probability of finding an electron here and here, we can think about that as this line in this diagram. Here is that barrier. But if I make that barrier thin, there's a probability of finding the lion inside the cage and outside of the cage at the exact same time. So all of this explains two things that you need to know. Alpha particle decay, there's a probability. We don't know when it's going to happen, but there's situations in which the alpha particle can exist outside of the atom as well as inside. That might explain how alpha particle decay happens. And scanning electron tunneling microscopy, which is a tool we use to visualize at the atomic scale. So when I was a scientist, I had this in my lab, and we'd make materials, and we can visualize materials at the atomic scale by bringing a single atom of gold in very close proximity with other atoms. And if I adjust the voltage right, what I can end up doing is creating a very similar wave function in the electrons here as the electrons in an atom. And if that's the case, the wave function on the outside overlaps with the wave function on the inside, and these electrons can simultaneously exist in both materials, creating a very strong current. So this scanning electron microscope, it moves a very thin tip, a single atom tip of gold along a surface, and as long as that gold gets close enough, it doesn't have to be touching, but close enough, and has the appropriate voltage to match the wave functions between the two materials, electrons will teleport or tunnel, okay, and get very fast currents. And then you'll be able, every time you get a current, that means you're above an atom. And so we can image a material surface at the atomic scale. So here's just a patterning of probably silver or something that's deposited as a single layer on glass, and we're able to image that organization at the atomic resolution using tunneling and scanning tunneling microscopy.